So this is going to be a really short video. I probably could have tacked it on to one of the previous videos, but it just felt different enough that maybe it deserved its own space. In the intro video to this section, maybe you remember that not only did we look at cases where the base was approaching infinity, but we also looked at cases where the exponent was approaching infinity for a given base. And I think of the different cases, that was probably the most challenging one, especially when we got into negative exponents, because we had to take advantage of some of these reciprocal rules. Well, we're finally ready to use that knowledge. What if we're evaluating the limit as x approached infinity of 7 divided by e to the x plus 14? The important thing to realize here is that e is a number that's roughly 2.7. It doesn't really matter what value e is. All that really matters for our purposes is that e is greater than 1. It's a positive number greater than 1. So when you go back to all these different cases, the base, which we use the letter a to signify, is greater than 1. So what happens if we take the limit as x approaches infinity of 7 divided by e to the x plus 14? Well, all the x's are getting arbitrarily large, but there's no x's up in the numerator. So the numerator is not changing at all. The numerator is just equal to 7. But down in the denominator, because e is greater than 1, if we consider the limit as x approaches infinity of e to the x power, we get something that approaches infinity. Again, that's this fact. If a is greater than 1, the limit as x approaches infinity of a to the x is equal to infinity. So I have the quotient of something that stays constant at 7 and something that gets infinitely large. What I'm describing is a case that we've seen before. It's a lot like the limit as x approaches infinity of 1 over x. The top is a constant, the bottom is getting arbitrarily large, and we already know that the limit as x approaches infinity of 1 over x equals 0, and by that same logic, the limit as x approaches infinity of 7 divided by e to the x plus 14 is going to end up being equal to 0. You'll quickly get to the point where you can just look at this and evaluate this limit, but I think especially early on, it's nice to be able to show your work. Unfortunately, these specific problems aren't very conducive to showing your work. I do have a way you can show your work, but it kind of makes me cringe when I show students how to do it, because it's not really proper notation. However, even if the notation isn't proper, I think the ideas that it conveys can be really useful, especially early on. So I'm going to do it, even though you should be careful writing what I'm about to write in a future math class, as your teacher might roll their eyes a little bit. The limit as x approaches infinity of 7 divided by e to the x plus 14 is 7 divided by infinity plus 14. You can't really write this because infinity is not a number, so it doesn't make sense to have it as an argument with addition and division. But this idea makes perfect sense because the limit as x approaches infinity of e to the x power is equal to infinity. I'm going to replace this e to the x power with this infinity symbol. Again, it's not proper notation, but hopefully you understand what I'm saying here. This limit acts like 7 divided by some infinitely large number plus 14. Well, an infinitely large number plus 14 is just some other infinitely large number, so this is just equal to 7 divided by infinity, loosely speaking, and when we have a constant divided by a number that gets arbitrarily large, the value of that expression approaches 0. It's a little bit strange to write these two equal signs in here, because infinity is not a number, it's kind of a concept. But I think I'd rather write some non-standard stuff than just go straight from the question to the answer, because even if this specific example seems pretty easy, I think what you'll find is they can get a little bit more complicated. Let me try to demonstrate that complication with part B. The limit as x approaches negative infinity of 7 divided by e to the x plus 14. Well, again, the 7 doesn't have any x's in it, it's just a constant, so when I evaluate the limit, it remains a 7. The limit as x approaches negative infinity of e to the x is equal to 0. Wait, what? Where did that come from? Recall from the intro video that if your base is greater than 1, which it is because e is greater than 1, when we take the limit as x approaches negative infinity of that base raised up to the x power, we get 0 as our answer. Think the limit as x approaches negative infinity of 2 to the x is the same as the limit as x approaches positive infinity of 1 divided by 2 to the x, because negative exponents act as reciprocals, and this limit is equal to 0. By that same logic, the limit as x approaches negative infinity of e to the x is equal to 0, so down on the bottom I got 0 plus 14. 7 divided by 0 plus 14 is just 7 divided by 14, which is just 1/2, which is what this limit evaluates to. A couple more examples, then we'll call this short video good. What about the limit as x approaches infinity of x to the fifth divided by e to the x plus 14. This is kind of an unfair question. We really currently don't have the machinery necessary to evaluate this limit. Because what's going on is when x gets infinitely large, x to the fifth gets infinitely large, and e to the x plus 14 gets infinitely large. So we kind of end up with an infinity divided by an infinity, and that's all sorts of confusing. What does that equal? Is that equal to infinity? Is it equal to 0? Is it equal to 1? Well, it turns out that it kind of depends, and to figure out what it's equal to, we'll need the techniques of the next section. However, fortunately, there is a shortcut way to get around evaluating these limits without the methods of the next section. And it's just to remember that exponents always beat powers. What do I mean by that? The limit as x approaches infinity of x to the fifth is really, really large, but it's nowhere near as large as the limit as x approaches infinity of e to the x power. In the same way that x to the fifth gets large quicker than x squared gets large, e to the x gets large quicker than x to the fifth gets large. You can kind of see that in Desmos. Here's y equals x to the fifth power, and here's y equals e to the x power. It might look like the graph in blue is getting big quicker than the graph in green is, but if you zoom way out, you actually see that that's not at all the case. The graph in green, y equals e to the x, gets bigger much quicker than the graph in blue does. The graph in green attains this height of 3 million, for example, at this point, somewhere right around 15, whereas the graph in blue doesn't attain that 3 million point until closer to 20. Exponents beat powers. And what that means in this example is that the denominator is going to get big much quicker than the numerator is going to get big. And when the denominator is bigger than the numerator, you end up with a value that approaches 0. Because exponents always beat powers, the limit as x approaches infinity of x to the fifth divided by e to the x plus 14 is going to end up being equal to 0. If that's really confusing right now, maybe just remember this fact, and trust me that in the next section I'll explain more about what's going on. Before I end this video, I want to consider one more example. It might look really similar to what we have above, except now we're not considering the limit as x approaches infinity. We're instead considering the limit as x approaches negative infinity. Again, we don't really have the machinery to solve this algebraically. We'll develop that machinery in the next section, but maybe for now we can just sort of think about what's going on here. The limit as x approaches negative infinity of x to the fifth, because a negative number raised up to the fifth power is a negative number, approaches negative infinity. Makes me feel a little bit uncomfortable, but I'm going to write equals negative infinity right here. What about down in the denominator? E to the x power, when x approaches negative infinity, approaches 0. That's a case we've seen a few times. Remember, as x approaches negative infinity, e to the x approaches 0. Loosely speaking, that's because e to the negative infinity equals, I don't feel comfortable writing equals here, 0. So down in the denominator, when I evaluate the limit, I get 0 plus 14. I got something that gets arbitrarily large, negative, divided by something that's positive. This limit evaluates to negative infinity. If these limits make you feel a little bit uncomfortable, I think that's good. I think they're kind of supposed to. That level of discomfort is something that we're going to work through in the next couple of sections so that when you see this in a Calculus 2 class, you're a lot more comfortable with it and you have all the background necessary to be successful in that class.